Thank you, Holly. Good
Thanks,
afternoon.
Norman.
Thank you. Good afternoon, everyone. Yes, let's get going. As Holly said, I work at NEL. I've been there quite a while, over 35 years, in fact. Background in thermophysical properties of fluids and flow-related activities. And what we're going to be talking about today links those. The title is Density, the other vital bit for flow measurement. So over the course of the webinar, I'm going to show you why density is important for flow measurement for liquids and gases. So I'll say something in terms of introduction about why it is important, and then we'll look at a range of density measurement techniques which are available. Also look at some of the calculation methods that can be used for certain applications, and then I'll wrap it all up, summary at the end. And as Holly said, we'll take questions if there's time at the end. If not, we will follow up if you have submitted questions and we don't have time to cover them in the webinar itself, we will follow them up later. So please, if there's anything isn't clear or you want to know more, submit a question and we will answer it. Okay, so let's take a step back and think, where would we need to know about density of fluids, gases or liquids? Well, many process applications use density for both process control and product quality assessment. So in that case, density is being used directly as a control parameter or a safety parameter, for example. You could use it, for example, in checking batch quality, batch-to-batch variations in a process. However, it's also the case that accurate flow measurement is vital throughout process industry. We tend to think that we live in a solid environment. I'm sitting at a desk looking at a screen. You'll be sitting on a chair, perhaps at a desk somewhere, solid environment. Well, for one thing, you're sitting in a fluid. That fluid is the air around you. But the solid environment that we interact with, a lot of it is actually processed in the liquid phase. So, the chair I'm sitting at, the arms have plastic coverings on them. The plastic is now solid, but during processing, it was processed in the liquid phase. And that's true for a vast number of things that we take for granted as solid objects in their final state. So accurate flow measurement is vital throughout process industry. It's also obviously vital in the energy industry, where the flow of the fluid is the primary thing of interest to how much gas or how much oil is being produced from a field. And then depending on the technology that you're using to measure the flow rate, you might be measuring by mass or by volume. But there is often a requirement to interconvert between these quantities. And that's where density comes in. It requires a knowledge of the density of the fluid as a function of temperature and pressure. So if it's a flow system we're looking at, a flow measurement system, and it has that requirement to interconvert from mass to volume or volume to mass, density therefore becomes a fundamental part of that flow measurement system. So what is density? Well, fairly simple. It's mass per unit volume. So nice, easy equation here. And in the SI system, therefore, the unit of density is kilogram per cubic meter. You'll also see other types of density units measured frequently, particularly in the oil industry and in certain other applications, food and drink sector. Sometimes you'll see relative density or specific gravity. Specific gravity is usually in oil related. Relative density. These are a density divided by the density of a reference, and the reference is at stated conditions. For liquids, the reference is often water at 1 bar and 4 Celsius. For air, it's often, for gases, it's often air at 1 bar, but at 0 Celsius. And it's important to note that relative density is not a ratio of densities. A density ratio is the ratio of the density of the fluid at temperature and pressure to the density of the same fluid at reference conditions. And there are lots of other types of density around. Proof, for example, is widely used in the spirits industry, API gravity in the oil industry, and there are interconversion equations between them. Simple one there for converting from API gravity to specific gravity or vice versa. So that's density, that's what density is. That's all well and good. How do we actually go about measuring the density of a fluid? So what I'm going to do over the next few slides is to have a look at a range of density measurement techniques, some of which are applicable to both gases and liquids, some of which are only applicable to liquids. And we'll look at the advantages and disadvantages of each of these techniques. But before getting down into the detail of techniques, it's worth, again, doing a little bit of a first split on them and saying we can think of them in two categories. We can think of offline methods. So these are ones where we take a sample from the fluid, the gas or the liquid, and we measure it separately in an offline device. Alternatively, there are online or inline methods, which may be either insertion or flow-through techniques, where the measurement is made effectively in the fluid that you're interested in. That also leads us on then to the question of calibration of all of these devices, either the offline methods or the online or inline methods, in particular if they are forming part of measurement systems, the other parts of which also require calibration. So how do we measure density? Well, primary standard for flow, for example, is effectively a bucket and a stopwatch. It's a bit more sophisticated than that. The facilities at NEL have very, very low uncertainties, but the principle is that you have a vessel and you fill it with the fluid that you're interested in. You either weigh the vessel empty and filled, so you then have a mass and a time, or you measure the change in volume of the liquid in the vessel, so you have a volume. So you can have a mass or a volumetric primary flow measurement. Density, essentially the same, but remember now we need both mass and volume. So we need to know the mass of the fluid that we have collected and the volume that it is occupying in the container. And that's as close as we can get to a primary measurement of density. Now, that sounds fairly straightforward, and at one level it is, but as you push down the uncertainty on the density that you're measuring, it becomes more and more difficult to achieve. In terms of the techniques that are available, I'm going to cover 5 techniques here, which, as I said, some of which are applicable to both gases and liquids, others of which are only applicable to liquids. Hydrostatic techniques are pretty close to what I was saying in terms of primary standard, in the sense that we are determining the apparent weight of a body of known mass and density totally submerged in the fluid whose density we want to measure. Archimedes' principle. Again, these can be broken down into broadly 3 implementations of the technique. A mechanical suspension system, where the body in the fluid is connected to a balance using a fine wire. Instead of the wire, you can have a magnetically coupled system, where you have a magnet and an electromagnet coupling the body to the balance. Or you can use a magnetic float system, where the body in the fluid is held in equilibrium by an electromagnetic field. And by controlling and measuring the field, you can effectively measure the apparent mass of the body in the fluid. What would one of these look like? Well, here's an example of a magnetically coupled system. So we have our body immersed in the fluid, the sinker, quartz, in this case, quartz glass sinker, and a coupling system which transmits its apparent weight in the fluid through the wall of the enclosure to a balance. And again, the equation is very simple at its most basic. The density is given by the difference between the true vacuum weight of the body and its apparent weight in the fluid divided by the volume of the body. Now, in practice, you have to apply second-order corrections, but in principle, it is that simple a technique and therefore very close to the primary method for determining density. Hydrostatic techniques have a number of advantages. They can, depending on the design and implementation, be automated. Again, depending on the design and implementation, they can be used over a wide temperature and pressure range. For example, the one we looked at in the previous slide, the whole system is inside a pressure vessel, inside a thermostat, so you can work across an extended temperature and pressure range. And they can be very accurate, 0.005 or perhaps even better over limited ranges to 0.02. So they are essentially a primary standard method. And again, depending on the implementation, if it's a closed vessel arrangement, they can be used for gases and liquids. Obviously, there are disadvantages. If you want to achieve those sort of uncertainties down at the 0.005% level, then it needs careful design and careful operation. If it's not automated, then it's time-consuming to use to get to that sort of level of performance. Conversely, automating it often means it's quite expensive, and they're really not suitable for online use. These are laboratory, into primary standard type devices. Going to the other extreme, pyknometers measure the mass of a known volume of fluid. So again, we've got the two quantities that we need to know for density, mass and volume. And again, there are various implementations of these. We've got capillary stoppered pyknometers, where you compare masses of equal volumes of sample and water. Graduated bicapillary pyknometers, which are calibrated using water and have a scale that you read. Or pressure pyknometers, again, often calibrated using water. And the pressure pyknometer is essentially the closed vessel, pressure capable version of the capillary stoppered pyknometer. So the capillary stoppered pyknometer on the left, small glass vessel with a plug lid which has a capillary through it, hence the name. And you fill the vessel, insert the stopper, the capillary allows the fluid to flow over the top to a defined level, and you can then weigh that with your reference fluid, water. Then you repeat with the fluid whose density you need to know. So you've measured two masses, you know the density of the reference mass, the water, and you can therefore calculate the density of your fluid of interest. Graduated bicapillary pyknometers, as I mentioned, have a scale, again, calibrate with water. Pressure pyknometer, you would weigh the pyknometer empty and then fill it with the fluid, which may be a liquid or a gas, and then weigh again. So again, you have two measurements of a known reference, water, usually. You get a theme here. Water is coming up as the reference fluid in a lot of these situations, even when we're potentially measuring other fluids. And the reason is that we know the density of water very accurately across a very wide range of temperature and pressure conditions. So it makes a very good reference fluid from that point of view. It has one or two other problems, particularly things like capillary effects, and also getting it back out of vessels. It can be quite difficult, but it has that very well characterized density as a function of temperature and pressure that we need for a reference fluid. Pyknometers are fairly fundamental. They are very simple devices, and therefore they tend to be fairly cheap to purchase. They can provide what I would class as good to reasonably high accuracy, possibly even down to 0.01%. And depending on the design, they can be used for gases as well as liquids if it's a pressure pyknometer. But to achieve those sort of levels, to get down below the 0.1%, does require careful operation. And generally, if that's manual, it comes down to having a very skilled operator. Also, if you're trying to do that, it tends to be time consuming if it's not automated. Again, like the hydrostatic techniques, they can be automated, but that obviously increases the cost. So you lose the advantage of them being cheap to purchase. And they're not suitable for online use. Pressure pyknometers are a hybrid in that you are taking a sample off and then measuring post the measurement. So it's not an online technique in that sense. So what can we use if we need to measure online? Well, oscillatory techniques are probably the most widely used way of doing online density measurement. And there you measure the oscillation period of a body, either immersed in the fluid or filled with the fluid. So filled with the fluid, it would be a vibrating tube where you measure the typically transverse oscillation period of the tube. And that changes as a function of the density of the fluid because you're effectively changing the mass of the vibrating tube and fluid. Or you can have an insertion type where you have a rod or a tuning fork immersed in the fluid, but again, in this case, the period of oscillation will also change as the density of the fluid changes. Insertion densitometers can be used for liquids or gases and are either inserted directly into the fluid or perhaps in a side stream or in a pocket, as shown here. And as I've mentioned, would either be a tuning fork design, such as the one on the top right there, or a thin-walled cylinder. Laboratory instruments most commonly tend to be small bore U-tube, but the principle is exactly the same. You're measuring the period of oscillation, which will change as a function of the density of the fluid. Flow-through devices are either dedicated flow-through vibrating tube densitometers or Coriolis meters. All modern Coriolis meters have density as their secondary output. So you get a measurement of mass flow and also density. But again, it's the variation of the period of oscillation with the density. Oscillatory techniques do have a number of advantages, obviously. In principle, they are simple and they are easily automated. They can, again, depending on the design, be used over wide ranges of temperatures and pressures, up to very high pressures, down to very low temperatures. And they can be used in line, which it really is their big advantage in terms of process applications and measurement system applications. And they are commercially available in a whole variety of formats to suit different requirements. Again, they can potentially be very accurate, certainly easily better than 0.1 down to 0.02 for certain types and certain applications. And again, depending on the design, they can be used for both gases and liquids. All of that comes with some disadvantages, the most obvious of which being they tend to be more expensive than things like pyknometers. But you get all of those advantages, particularly the online or inline use. However, they do require careful calibration, again, if you're going to try to achieve those low uncertainties in use. A couple of other techniques to look at: compression techniques, where we measure the change in length of the fluid. That can be done in a number of ways. It can be a capillary rise, where you measure the change of the height of a liquid, and this one's only applicable to liquids, obviously, in a capillary tube. Or you can use piston displacement, where you measure the displacement or change in position of a piston in a pressure vessel. So that one you can apply to liquids at pressure. Similarly, a sealed bellows approach, where you fill a bellows with the fluid whose density you want to know. You know them, therefore you can measure the mass of the fluid there. and you can measure the change in length as a function of pressure or temperature. So these techniques are only suitable for liquids. Sonic techniques measure the speed of sound in a fluid, and you can either use an interferometer with a variable path length, which detects the impedance of the vibrating crystal, which is a function of the speed of sound, or an optical diffraction technique, which measures the diffraction of the light beam through the density variations caused by the sound wave. And there is a fundamental thermodynamic relationship between density and speed of sound. So you're measuring speed of sound, but you can relate that to the density. And these techniques can be used for gases and liquids. So we've seen a range of techniques which can be used to measure the density of gases and liquids. For general lab and process applications, oscillatory techniques are the most widely used and the ones that you're most likely to come across as a user. The other techniques, particularly the hydrostatic weighing techniques, tend to be the preserve of primary standards laboratories or research groups. But it's also worth pointing out that although I mentioned that some of these systems can be fairly expensive, whilst that implies that high accuracy, if you want to achieve it, will generally mean high cost for the equipment, the converse is not necessarily true. Simply because a device has low accuracy doesn't necessarily mean it has low cost. It might just not be a good implementation, or indeed even the appropriate method to use for the system that you're interested in. So I mentioned earlier that in particular for online or inline densitometers, which are forming part of a measurement system, calibration is important, because recalibration at appropriate intervals is vital for maintaining the traceability. And these calibration requirements are often driven by regulations. Equally, the calibrations must be fit for purpose. And I'll explain a bit more about what I mean by fit for purpose as we go through this section. So, as I said, the requirements are often driven by legislation. In the UK, for liquid measurement systems for petroleum, the requirements from the OGA, the Oil and Gas Authority, UK Oil and Gas Authority, specify an uncertainty of 0.25% by dry mass of the quantity exported into common transportation systems, pipelines. And you know, that's by dry mass. Now, although it is changing, a significant number of the liquid measurement systems in the North Sea still make use of volumetric flow meters. The original installations used turbine flow meters because they were the best available at the time, and they're volumetric. But you have to report your production by mass, and allocation in shared transportation systems is also by mass. So fluid density is required to convert from the volumetric output of the flow meter to the mass required by the regulator or the pipeline. And the most commonly used technique are vibrating tube densitometers. But now, if they're forming part of the measurement system to achieve that 0.25% specified by OGA, traceable calibration of the densitometers as well as the flow meters is therefore also required. Fit for purpose. Well, let's take a step back. Previous approach in this area was that the manufacturer would undertake an initial calibration of the densitometer, typically at ambient conditions, i.e. 20 Celsius and 1 bar, and then derive corrections for other temperatures by making measurements at 1 bar at other temperatures, and pressure corrections by making measurements at other pressures at 20 degrees, but not simultaneously. Recalibrations, particularly if done by third-party laboratories, were typically only done at 20 degrees and 1 bar, assuming that none of the pressure or temperature coefficient effects had changed. But of course, densitometers are used at non-ambient conditions, and the equation that is used for the most commonly used ones is cross-coupled in the period, the output of the densitometer, the temperature, and the pressure. And this led to some concerns about the appropriateness, the fitness for purpose of the previous calibration approach. And as a result of that, NEL led a joint industry project to examine the effects of temperature and pressure cross-coupling on liquid densitometers for the UK sector of the North Sea. Following that, OGA, as it is now, changed its guidance and requires densitometers to be calibrated at their anticipated operating conditions, i.e. simultaneously at temperature and pressure, so ensuring the calibration is fit for purpose. So how do you calibrate a densitometer? Well, again, like all of these things, in principle, it's simple. You use fluids of accurately known density. The fluids, of course, have to cover the full operational density range that the device will see in service. The fluids probably also have to cover other relevant parameters, in particular viscosity and speed of sound, since these are admittedly second-order effects on oscillatory densitometers. And the fluid properties obviously must be known across the full temperature range and pressure range required, because the fluids are acting as your transfer standards. So at the start of the GIP, we asked the sponsors, okay, what sort of range of conditions, in particular for density and viscosity, do we need to cover for the North Sea? And you can see here that the full range went down to about 550 odd kilograms per cubic meter, which will be condensate type applications, up to almost 1200 kilogram per cubic meter, so high viscosity heavy oil, and corresponding with the viscosity ranges from centipoise or below up into the 40 plus centipoise for the high viscosity oils. But the most common range was a much smaller subset of that. So what we tried to do were find reference fluids which would basically bracket that common range. So once we had identified fluids, we then had to determine their density as a function of temperature and pressure across the required range. And to do that, we used the NEL primary liquid densitometer. This is the one that we saw earlier. It's a single sinker magnetic suspension densitometer. We've seen that equation before based on Archimedes' buoyancy principle. Our particular implementation can achieve an uncertainty, an expanded uncertainty of better than 0.015 at 95% confidence across the temperature range from -40 up to 150 at pressures up to 300 bar. Across more limited temperature and pressure ranges, the uncertainty is 0.01% or slightly lower. And here we can see it in a bit more detail. So previously we just saw the little bit showing the sinker in its measuring cell. That's a pressure vessel, which is in turn is sitting inside a thermostated vessel. So we can control both the temperature and the pressure of the fluid that we're interested in measuring the density of by measuring the apparent weight of the sinker. And the apparent weight of the sinker is read by the analytical balance coupled through the wall of the pressure vessel by a magnetic suspension coupling system. That's all well and good. How does it perform? Here's three sets of data from measurements made using the system during the joint industry project. The measurements were made on 3 separate samples of reference fluid from different batches of the sample from the supplier. They were made across the period between August 2007, September 2008, so quite a time difference between them. And I've just picked the data at 20 and 100 Celsius here as the extremes of the range. And you can see that the agreement between 3 sets of measurements is very good. It's generally within plus or minus 0.005% or better. Okay, so the system's self-consistent, but we could have some bias in there that we haven't noticed. How do we deal with that? Well, by looking at measurements made by other people using other systems. So here's a couple of sets of data comparing measurements from PTV, the German standards body, and by the corresponding US one, NIST, National Institute for Standards and Technology. And you can see that the agreement between, and this is for the same reference fluid, the agreement between the NEL and PTV measurements looks very, very good, which possibly isn't surprising in one sense, in that both systems were of the same design. The results, the comparison to the NIST data look a bit further off, and I was initially a little bit concerned about that. But when I looked in a bit more detail at the NIST data, I found that those headline figures we looked at on the previous page actually consisted of 3 sets of data, 3 sets of measurements from NIST, one of which was what they call their standard reference material, which is what they normally supply to customers as a reference material. One was an air saturated sample and one was a degassed. And you can see there that the difference is biggest for the air saturated and least for the degassed. Now, our system is effectively running degassed, so the measurements are close. We're generally within plus or minus 0.008%. Slight temperature effect, but much better than just a headline. So that gave us confidence that our reference measurements were good. That means we can move to the next stage. Fill a densitometer with 2 or more of these fluids, control the temperature and pressure of the fluids, and measure the output period. How good do we have to control? Well, temperature stability about 50 millikelvin, pressure stability about 100 millibar. Then measure the temperature with an uncertainty of about 15 millikelvin, ideally. Measure the pressure with an uncertainty of about 20 millibar. And because of the temperature and pressure stability, the output period should be stable to, in the nanosecond type range, and measuring periods to that uncertainty is easy. What does it look like in practice? Our system, we have an enclosure. The photo on the left shows a typical densitometer installed in the enclosure. The schematic on the right shows that we have a fan and a temperature control system below with which we can control the temperature of the air in the enclosure. Separately, we have a circulating loop whereby we can control the temperature of the fluid in the densitometer as it flows round. And we need to control both the air temperature round the densitometer and the fluid temperature to achieve those low uncertainties in temperature that I mentioned earlier. If we didn't control the air temperature when running at high fluid temperatures, you would have an unacceptable temperature gradient across the densitometer. Obviously, we can actually look at that in more detail and look at the uncertainties. And here's an example from our top level uncertainty budget for the facility. Just picked a set of conditions here. So we're running with a fluid temperature of 90 Celsius at 90 bar gauge, 91 bar absolute. And you can see that on the basis of our measurement capabilities, we're achieving our targets. Our temperature uncertainty is 12 millikelvin, uncertainty in the pressure is 20 millibar. Densitometer period uncertainty is down in the fractions of a nanosecond, as I mentioned. And the reference fluid density is below 0.01% here. So we will have good confidence that we're seeing the performance of the instrument when we look at it. Following on from the JIP, we started a calibration service, and since then we've calibrated over 750 of the 7835 series densitometers, which are still the most commonly used type in the UK sector of the North Sea. These have been calibrated to the current OGA guidelines. Operating conditions for these units we've seen ranging from 5 Celsius up to 95 Celsius, and pressures from 5 bar or even lower 3 bar up to 130, 131 bar A. Initially, what we found was that about half, so for about the first couple of years, about half of the units coming to us had as found errors of between -0.1 and +0.1%. But just saying that headline figure kind of masks the scale of the problem, because whilst about 15% had negative errors which were more than -0.1, about half actually had positive errors which were over 0.1, i.e. a significant number were overreading by a significant amount. Over the years, that has reduced as the calibrations have improved to become more fit for purpose from ourselves and from other calibration laboratories. Interestingly, there was no clear correlation between the as found error and operating temperature and pressure, which had been one of the things that had triggered the GIP in the first place. But what we also found was that just adjusting the base coefficients as per the previous procedure often wasn't good enough. Many of the units still had significant residual errors. So it was necessary to optimize more of the coefficients across a limited operating range to get down to the low uncertainties. Okay, so we've looked at measurement techniques, but in a kind of abstract way. What happens when you're actually doing it in practice? There are other considerations and other things that might affect the performance of your measurement system, even a well-calibrated one. Potential sources of error would include non-representative samples, if you're actually taking a sample offline. If it's an inline or online system, if you have inhomogeneity of the sample in the sensor, gravitational settling perhaps of two fluids of very different density, solid deposition onto a sensor, an inline sensor or online sensor, or conversely erosion, because deposition and erosion will alter the oscillating mass, which will therefore alter the apparent density. If it's a liquid we're looking at, if you've got gas breakout, then again that will cause a problem for the measurement. Stress effects. These are oscillatory systems. If they are subject to stress, either in use, perhaps by an excessive pressure event, or stress when taken out of use by mishandling or damage, that will affect their temperature, either pressure and temperature dependence. And if it's part of a measurement system, then temperature and pressure differences between the densitometer and the flow rate will also have an effect. So that's measurement. Let's have a quick look at calculation. And specifically, we're looking here in terms of the oil industry, because crude oil and petroleum products are typically sold by volume at reference conditions. The reference conditions are either 60 degrees Fahrenheit and 0 psi gauge for imperial, or 15 Celsius and 1 bar for metric. So the effects of the temperature and pressure on the fluid density are required to convert from the measured conditions to the reference conditions. And this is usually done using things called volume correction factors, which have been developed to simplify that calculation. The most widely used of which are the ones developed by and maintained by the American Petroleum Institute. And they've got a fair history. The most widely recognized starting point were the 1952 Blue Book tables. They were then revised in 1980, and then again in 2004 as part of the Chapter 11 measurement series. The 52 Blue Book was called the Blue Book for a very obvious reason. It was a blue cover, and it was actually a joint publication between the American Society for Testing of Materials and the UK Institute for Petroleum. Interestingly, although it was published in 1952, a lot of the data in it were based on crudes and fractions published in 1916, most of which were primarily from UK domestic production, US domestic production at that time. The 1980 revision had some improvements, better base data in particular, and data handling in terms of the database. It covered just over 65% of worldwide production and about 68% of estimated reserves in 1974. So a bit of a lag, but not as bad as between 1916 and the 52 Blue Book. And again, better handling of the data. The tables were replaced by equations, and there were also statistical studies carried out to check the data. The 2004 correction did away with the printed tables completely. It extended the temperature and pressure ranges and introduced the use of combined temperature and pressure corrections. And as I mentioned, they're widely used in trade applications, but they can also be used in things like provers, where you need to convert between a volume in a volumetric prover and mass if you're calibrating or proving a mass flow device. So again, as I mentioned, for densitometers, you really want a small temperature and pressure difference between the prover and the device you're testing. But even if you achieve that, how do you convert from the volume from your volumetric prover to your mass? You do it using the conversion factors. So we've got an equation here relating the base prover volume, a reference, through to the quantity we're interested in, the mass, which makes use of these conversion factors. There's also a couple of other terms in there to account for the effect of temperature and pressure on the volume of the reference. So that can also be written in terms of fluid densities, and the fluid densities can be expressed in terms of these volume correction factors. In the case of the temperature correction, we have a thermal expansion coefficient term and temperature differences. Compressibility term, we have a compressibility coefficient. The thermal expansion and compressibility coefficients were correlated in terms of base density for the oil samples in the Blue Book tables, the 1980 revisions, etc. So there's an expression there for the thermal expansion coefficient with a series of coefficients. And there are several coefficients depending on the liquid's classification and its density at the reference temperature. The compressibility equation has one set of coefficients for all fluids, regardless of their classification. In terms of the temperature classification, the Chapter 11 classification has three categories: crude oils, refined products, or lubricating oils. There is an additional special application if none of the above apply, and that requires a knowledge of the thermal expansion coefficient determined by experiment. Just out of interest, we decided to have a look at how good they were in relation to our EPAT facility, our elevated temperature and pressure facility at NEL, which uses a compact prover as its reference, but calibrates Coriolis meters, so mass flow devices. So looking at one of the oils that we use in that facility, we modeled it using the conversion factors, treating it first as a generalized crude. And you can see at 20 Celsius, it doesn't look too bad across the pressure range between minus 0.05 and plus 0.08%. Time you get to 50 degrees, the errors are getting a bit bigger, and by the time you get to 75 degrees, you're up or down to minus 0.7 or so. And EPAT can operate to that temperature, so treating it as a generalized crude doesn't work. Refined product improves it a bit, but still not enough. Okay, let's treat it as a special application. Aha, that looks better. Until you realize that, well, no, because we need to get density as a function of temperature and pressure to something of the order of 0.04% across the full operating range of the EPAT facility. It's actually not surprising that they struggle there, because if you look in the standard, the Chapter 11, buried in Appendix B, there's a little bit which says that the limits were only up to 49 bar for the pressure data, and it was extrapolated beyond that. So that's kind of says, well, can we do better? Yes, we can if we write it in terms of density, and we have expressions for the density as functions of temperature and pressure. And you can come up with an equation that will relate the density of a fluid to its temperature and pressure across a wide temperature and pressure range. Here's an example of an equation that we use. So given a good set of measurements from a primary standard or a reference densitometer, this equation would fit the density with an uncertainty of 0.03% across a fairly wide range, more than enough for EPAT, for example. So we can do better, but you need a lot of data to generate a fit like that, and the coefficients are fluid specific. So that sort of equation isn't an ideal replacement for the API correlation. It should be considered if you're using it as part of a reference measurement system, as we do on EPAT. Equally, the limitations of the API method should be addressed, and there are techniques that can help there. So in terms of calculation methods, the API volume correction factors are widely used to convert from measured to reference conditions. They are fit for their original purpose, but not really if you're going to use them as part of a primary reference system. Alternative approaches can provide lower uncertainties. What about gases? Well, for pure components or certain mixtures, say pipeline quality natural gas, the easiest and most accurate method is to determine the density. To determine the density is to measure the temperature and pressure of the gas, then use an appropriate equation of state. So for pure components, there are a number of packages around. NEL's PPDS, Thermal Physical Property Data Service package, the NIST RefProp package. These will give you, depending on the temperature and pressure range and the fluid, the gas, these will give you densities with uncertainties of 0.02 to 0.05%, better than you will easily measure. Natural gas mixtures, AGA8 is the most widely used, or the GERG, both of which will give you uncertainties of 0.01 to 0.05, or possibly better. And they work for a 21 component defined range. But for mixtures, you need to know the composition to be able to use the equation of state, which you can get either by measuring online, using online chromatography, or by taking samples offline and measuring again using a chromat. If you don't know the composition, or the composition is out with the limits of the equation of state, then you have to use an online densitometer technique. And there's a lot of interest currently in the carbon capture, utilization and storage applications, and in hydrogen for decarbonizing the gas grid. Now, for pure CO2 and for pure hydrogen, again, the easiest and most accurate methods is to measure the temperature and pressure and use an equation of state. For pure CO2, for example, the Span and Wagner equation will give you the densities, again, more accurately than anybody but a primary standard laboratory could measure. However, for carbon capture, utilization and storage, it's unlikely to be pure CO2. There will be contaminants depending on the source of the CO2 and the capture process. In general, these will be low amounts, but even small amounts of certain contaminants can have significant effects. So again, you would need to know the composition either by measuring it or by knowing from some other method the input compositions. Similarly, in the gas grid, there's a lot of interest at the moment in looking at blends of hydrogen with natural gas up to 20%. Up to that limit, you don't need to change burners, etc. So there's a certain incentive to go down that route. But again, that means that you're having to use equations of state. Composition needs to be known. You've got the advantage in the gas grid systems, you know how much hydrogen you're putting in, so you know what the composition is. But the problem is that equations of state generally don't like hydrogen in the mixtures, so they often struggle to give you good results. Similarly to liquid measurement systems, there are a number of practical considerations which can trip you up if you're not careful. Potential sources of error include problems with the calculation approach if you are using sampling and an equation of state. If, as with liquid systems, you don't get a representative sample, then the answer will not be correct. And representative sampling for gas systems, whilst it should be easier than for liquids, can still present challenges. The use of an inappropriate equation of state is also another concern. Some equations of state are good for some properties, but not for others. And it's not appropriate just to say, I'll always use this equation for all my property calculations, because whilst it might be the best for some, it might struggle for others. But even if you have used an appropriate equation of state, it may just have limitations for the application that you're using it for. Either, as I said, in the case of AGA 8 or GERG, they are limited to a set of 21 components. If you have components in your mixture which are outside, are not within that set of 21, then the equation will calculate, but it will have some residual error. Similarly, as I mentioned in the previous slide, hydrogen causes problems. Now, even with direct measurements, you can have problems too. Again, solid deposition on center elements or erosion of center elements will alter the oscillatory mass because it will be oscillatory techniques. You might say, oh, how are you going to get erosion in a gas system? Well, we've seen examples in the past of gas systems, gas flow systems, which have had solid content causing erosion, not in this particular case of a densitometer, but actually knocking a hole in the bend of a pipe. So you can get solid problems in gases leading to erosion or deposition. And the converse of the liquid system, where breakout of gas causes a problem. If you get liquids in a gas densitometer, again, that will affect the performance of the densitometer. And as for the liquid systems, stress effects, either because of overpressure events or mishandling, will alter the performance. And again, if the densitometer is part of a combined flow measurement system, temperature and pressure differences between the densitometer and the flow meter will cause problems if you don't account for them correctly. So let's summarize. Hopefully, over the past hour or so, we've seen the importance of density for flow measurement systems, starting from this position that because flow measurement is vital throughout process industry and energy production, we need to be able to measure flow accurately, but depending on the technique used, there is often a requirement to convert between mass or volume. And that requires the knowledge of the density of the fluid as a function of temperature and pressure. We've looked at a range of density measurement techniques for gases and liquids, wide range commercially available. But again, whichever technique is chosen, appropriate calibration is vital. And calculation methods are also important if you have to express density at alternate conditions, going from measured conditions to reference conditions. Density is also used, as we said, directly for process control and process quality applications in many systems. So it really is a very fundamental part of the process industry and energy production, primary energy sector. And just to put it into context in terms of the national measurement system, density determination essentially sits at the core of all of the capabilities that we have at NEL, which form part of the UK National Flow Measurement Standards facilities. If you look at any of our facilities, we require density. In the case of our advanced multi-phase facility, for example, there is a separation system there which separates the gas phase and the two liquid phases, the oil and water. The liquid phase separation is very good, but it can never be perfect. So we need to account for the small amounts of oil in the water and water in the oil. And we do that through online measurement of the density and offline measurement of the density of the pure fluids, and we can calculate. So density is used there. EPAT, I've already mentioned, it uses a volumetric reference, but it is typically calibrating mass flow meters. So density is used directly there. So density sits at the core of the UK's national flow measurement capabilities. And hopefully that's given you an idea of the importance of density.
Thank you very much, Norman. Fantastic as always. Now we're almost just about out of time, unfortunately. However, we'll maybe squeeze in a couple of questions, Norman, if that's okay.
Yeah, that's fine.
Okay, we've got some coming through just now. So, how good is the density output of a Coriolis meter?
Potentially very good. Some of them, depending on the temperature and pressure range and the calibration, you can easily achieve 0.02%, possibly even slightly better. So they are now actually very good on density output.
Okay, well, that's actually another good. Why do we need density if we're using a Coriolis meter and reporting by mass?
That's a good point. If you are only interested in the mass, then you don't, but frequently you do still need to convert. One application, for example, would be, again, shared pipelines. Whilst the allocation is by mass, as I mentioned, if you've got a Coriolis, you've got that quantity. The pipeline operator also charges you a tariff based on the volume you're putting through. So you need the volume, so you need the density. So you still need the density output of that Coriolis meter to give you a volumetric flow rate for the tariff for the pipeline. Just as well the Coriolis does both for you.
Okay, Norman, I'll just squeeze in one more for you if that's all right.
Yeah.
What are the limitations of equations of state with hydrogen?
Right, that's a good one. I mentioned the Span-Wagner equation for CO2. For hydrogen, the Leachman equation, a similar form of equation, reduced Helmholtz equation, across the temperature range, say from 25 to 175 Celsius and up to 300 megapascals, so 3000 bar, it has an uncertainty in density of 0.04%. Great. The problem for mixtures is the mixtures, the equations are written in terms of things called reduced quantities, and the reduced quantities use critical parameters of the fluids. The critical properties of hydrogen are so different that the ratios are so much different from the other components, the methane, etc., and the natural gas. And mathematically, the equations struggle. If you run the RefProp package, for example, and specify a mixture with hydrogen, it pops up a warning saying this might not solve. It generally does. PPDS does as well, but that's the limitation. It's a function of the chemistry and the maths, really. So mixtures with hydrogen are difficult. We're having to look at that for our domestic gas metering rig that we've just built at NEL, which can look at hydrogen and natural gas mixtures, for example. So that's a very good question, very topical question, that one.
Yep. Okay, like I say, we're just about out of time. So thanks again, Norman. And thank you everybody for joining us today. Much appreciated. And as I mentioned earlier on, we will be sending you a copy of the presentation and the recording. Please feel free to visit our website. And if you have any other questions in general, just please feel free to contact either myself or Norman. We will do our best to answer all questions. And basically, just on behalf of myself, I'd just like to thank you all for joining us today. And I hope you all stay safe, as they say. Thank you.